Good morning, everyone, and welcome. I'm delighted to have you here today. Today, we will be discussing the validation protocol for 70% isopropyl alcohol disinfection. My name is Dr. S.K. Singh, and I hold a PhD in this field. In this presentation, we will go over the key steps and considerations to ensure effective disinfection using 70% isopropyl alcohol. We'll cover the protocol details, validation methods, and important best practices. So, let's get started and explore how to maintain high standards of hygiene and safety. In this slide, we're focusing on the objective of our study, which is to establish documented evidence that 70% isopropyl alcohol, or IPA, is effective in reducing microbial contamination on cleanroom surfaces. This is crucial because maintaining a sterile environment is vital in our industry, and we need solid proof that the disinfectant performs as expected under real-world conditions. Moving on to the scope, this protocol isn't limited to just one area or one type of surface. It applies to all classified cleanroom zones, whether they are grade A, B, C, or D, covering ISO 5 to 8 environments. We are looking at various surfaces, including stainless steel, epoxy flooring, glass, and polymeric materials. These are common in cleanroom settings and are often exposed to contamination. Finally, the disinfection methods considered here are spray and wipe, as well as mopping. These are typical application techniques used in daily cleaning routines, and our goal is to verify the effectiveness of 70% IPA across all these parameters. Connecting all of this back to our overall theme, this comprehensive scope ensures that our findings will be relevant and applicable across different areas, surfaces, and cleaning methods within our cleanrooms. Let's take a moment to look at the references that underpin our standards and practices. First, we have the EU GMP Annex 1 from 2023, which provides comprehensive guidance on manufacturing practices within the European Union. Next is USB 1072, which covers disinfectants and antiseptics, emphasizing proper use and effectiveness. We also refer to the WHO Technical Report Series 961, specifically Annex 6, which offers global standards on sterilization and contamination control. Lastly, ISO 14644 relates to cleanrooms, outlining classification and control measures essential for maintaining sterile environments. These references are crucial because they form the foundation for our quality and safety protocols. They help ensure that everyone involved understands the standards we need to meet and the importance of adhering to them. Now, moving on to the next part, responsibility. It's important to recognize that maintaining compliance isn't just about following rules. It's about accountability at every level. Each of us has a role in ensuring that the processes are followed correctly, that standards are upheld, and that safety is prioritized. By understanding these key references, we reinforce our commitment to quality. And by embracing responsibility, we ensure that our practices remain consistent and reliable, ultimately protecting patient safety and product integrity. Let's take a look at the materials and equipment we'll be using for this part of the experiment. First, for disinfecting our work surfaces and tools, we'll use 70% isopropyl alcohol, which should be sterile and filtered to ensure effectiveness. This is crucial for maintaining a sterile environment and preventing contamination. Next, we have our test organisms, including Staphylococcus aureus, Pseudomonas aeruginosa, Escherichia coli, and Bacillus subtilis, which is a spore former. These bacteria are commonly studied because they represent different types of microbes, some pathogenic, some more resilient, and they help us evaluate the disinfectant's efficacy. Moving on to the equipment, we'll be using sterile swabs to transfer samples, contact plates with tryptic soy agar, or TSA, for culturing, and an incubator set between 30 and 35 degrees Celsius to promote bacterial growth. Micropipettes will help us handle precise volumes of liquids, which is essential for accuracy in our testing. Lastly, neutralizing broth is included to stop the disinfectant's action at specific points, allowing us to accurately assess its effectiveness. All these materials and equipment are interconnected in our goal to thoroughly evaluate disinfectant efficacy, ensuring safety and sterility in our procedures. Now, let's move on to slide 6, where we define some key terms that are essential for understanding our methodology. First, we have log reduction, which is a way to quantify how much a disinfectant reduces microbial presence. It's expressed in log 10, meaning each unit decrease corresponds to a 10-fold reduction in microbes. Next, CFU stands for colony-forming units, which is simply a measure of viable bacteria or fungi that can grow into colonies. And finally, contact time refers to how long the disinfectant must remain wet on the surface to be effective. These definitions are fundamental because they help us precisely measure and communicate the effectiveness of our disinfection process. Now, let's look at how these concepts fit into our overall methodology. Now, let's move on to the disinfection procedure. First, you'll want to apply 70% isopropyl alcohol, or IPA, using a combination of spray and a sterile wipe. It's important to ensure that the entire surface is thoroughly covered with the disinfectant. This helps guarantee that all potential microorganisms are properly addressed. Next, you need to maintain a defined contact time, which is typically about 1 minute. This allows the disinfectant enough time to work effectively. Remember, thorough coverage and sufficient contact time are key to successful disinfection. Once the contact time has elapsed, the next step is to recover any remaining microorganisms. You can do this either by swabbing the surface or using contact plates. The goal here is to collect samples for further analysis. After collection, transfer these samples to a neutralizing medium. This step is crucial to stop the disinfectant's action and preserve the microorganisms for incubation. Finally, for incubation, place the plates in an environment maintained at 30 to 35 degrees Celsius for 48 to 72 hours. This temperature range is optimal for encouraging microbial growth, allowing us to assess the effectiveness of our disinfection process thoroughly. Overall, these steps form a critical part of ensuring that our environment remains hygienic and safe. Now, moving on to slide 9, let's talk about acceptance criteria. These are the specific conditions that a product or feature must meet to be considered complete and acceptable. They serve as a clear benchmark for success and help ensure everyone is on the same page about what's expected. Acceptance criteria are crucial because they guide development and testing, reducing misunderstandings later in the process. They also help us verify that the delivered solution actually solves the problem we set out to address. Next, we have controls. Controls are the safeguards and measures we put in place to manage risk and maintain quality throughout the project. Think of them as the checks and balances that keep everything on track, ensuring that processes are followed and standards are met. Implementing effective controls is essential because it helps us identify issues early, prevent errors, and ensure compliance. Together, acceptance criteria and controls form a strong foundation for delivering successful, high-quality solutions aligned with our overall project goals. Let's walk through an example calculation to understand how we determine the log reduction. We start with an initial microbial count of 1 million CFU, which is written as 1 times 10 to the 6. After treatment, the final count drops to 100 CFU, or 1 times 10 to the 2. To find the log reduction, we use the formula, log 10 of the initial count divided by the final count. So, that's log 10 of 106 divided by 102. Since dividing powers of 10, we subtract the exponents, giving us log 10 of 10 to the 4. And the log of 10 to the 4 is simply 4. This results in a 4 log reduction, which indicates a significant decrease in microbial load. Importantly, this reduction meets the acceptance criteria for effective microbial control. Now, to clarify the formula itself, the log reduction equals the log base 10 of the initial count over the final count. This formula is essential because it provides a standardized way to measure how effective a decontamination process is. By understanding this calculation, we can better evaluate and compare different sterilization methods within our overall quality control measures. In this slide, we're focusing on the hold time study, which is crucial for evaluating the stability of our IPA over time. We'll assess the product at several key time points: 0 hours, 24 hours, 48 hours, and 72 hours. This helps us understand how the IPA performs during typical storage periods. At each of these intervals, we test for two main things: microbial contamination, to ensure the product remains sterile, and efficacy retention, to confirm that the antiseptic properties are maintained throughout the hold time. By doing this, we can confidently determine if the product remains safe and effective during its intended shelf life. Now, moving on to the study matrix, which provides the framework for how we organize and interpret these tests. It's essentially our roadmap, ensuring we cover all necessary conditions and variables to validate the stability and efficacy of our formulation. Together, these studies reinforce our commitment to delivering a reliable product that performs consistently from production to use, supporting the overall theme of quality and safety in our formulation process. Now, let's talk about deviation handling. It's crucial that any deviation from our standard procedures is properly documented, so we always have a clear record of what happened. Investigating these deviations is equally important. We need to understand the root cause to prevent future issues. And of course, no deviation should be closed out without approval from the QA team, ensuring that everything stays compliant and under control. Moving on to change control, this is about maintaining the integrity of our process when any modifications are made. If there's a change in disinfectant concentration, for example, revalidation is required. The same applies if we introduce a new surface or change the method of application. These steps are vital because they help us verify that the process remains effective and consistent despite changes. Overall, these procedures are key to maintaining quality and compliance, ensuring that any adjustments are carefully controlled and validated to keep our standards high. Now, let's take a look at slide 11, which focuses on documentation. As you can see, it's crucial to keep detailed raw data sheets throughout the process. These sheets record the original data collected during testing, ensuring transparency and traceability. Incubation records are equally important. They document the conditions under which tests are conducted, helping us verify that everything was performed correctly. Calculation sheets are used to process and analyze the data, providing a clear picture of the results. Finally, the final validation report summarizes all these elements, offering a comprehensive overview of the validation process. Moving on to slide 16, which covers the conclusion criteria. Here, the key point is that the disinfectant is considered validated only if it meets specific acceptance criteria across all tested surfaces and organisms. That means no matter what surface or microorganism we test, the disinfectant must perform consistently within the predefined standards. Additionally, we look for the absence of any adverse trends in the data, so no signs of decreasing efficacy or unexpected results over time. When both these conditions are satisfied, we can confidently conclude that the disinfectant is validated and ready for use. This process ensures that our disinfection procedures are both effective and reliable, aligning with our overall goal of maintaining safety and hygiene standards. Now, let's take a look at the data record sheet, specifically the annex section. This part is crucial because it ensures that all the information we've gathered is properly documented and approved. When we talk about approval here, we're emphasizing the importance of validating the data before finalizing it. This step helps maintain accuracy and accountability throughout the process. It's essential that the relevant authorities or responsible persons review and sign off on this data. By doing so, we guarantee that the data is reliable and ready for the next steps in our project. Remember, thorough approval not only supports transparency, but also helps us avoid potential issues down the line. Ultimately, this annex serves as a formal record, confirming that everything has been checked and approved appropriately. For further support, please don't hesitate to reach out to us. We're here to help and provide any additional information you might need. Feel free to contact us through the provided channels. And with that, I want to thank you all sincerely for your time and attention today. Your engagement is truly appreciated, and I hope you found the presentation valuable. Thank you once again.